Welcome back to the Mapscaping podcast. My name is Daniel and this is a podcast for the geospatial community. My guest on the show today is Qiusheng Wu. Qiusheng is an associate professor at the University of Tennessee, senior research fellow at the United Nations University Institute for Water, Environment and Health, a visiting academic at Amazon, and the creator of GeeMap, a Python package for interactive geospatial analysis with Google Earth Engine. And that's what we're talking about today. We're talking about GeeMap. But there is another part to Qiusheng's story as well. It is the story of someone who saw something that was broken, and instead of pointing at it and saying, hey, this is broken, he fixed it. He fixed it for himself, he fixed it for his students, and then he shared it with the world. Qiusheng will be the first to tell you that his intention was never to become famous, but he kind of is famous. He didn't do this hoping that Google would recognize his contributions and support his work, but it happened. When he started working on GeeMap, the promise was not, if you do this, the biggest players in the world will notice you and want to work with you. But they have, and they do want to work with Qiusheng. This is the second time Qiusheng has been on the podcast. The first time he gave us a great introduction to Google Earth Engine, and you will find a link to that in the show notes of today's episode. Through this podcast, I have the opportunity to share conversations with lots of people like Qiusheng, people who have an outsized impact on the geospatial community because of the work that they do, or because of the way they champion ideas that are helpful. And notice the emphasis here is on the word helpful. But I can't do any of this by myself. And when companies like Planet show up and say, hey, we want to help, I'm really, really grateful. If you haven't heard about Planet before, go back through the archives and look for an episode called Planet, Imaging Everything Every Day, Almost. And if you have already listened to that episode, you will remember that Planet images the Earth every day to create a living data set of global change, and you don't need to learn new tools or take a ton of time to use the latest insights. You can use Planet satellite imagery to drive richer analysis with high spatial resolution, high frequency data, broad area coverage and automated detection feeds integrated directly into your geospatial platform. You can learn more at planet.com/GIS. There'll be a link to that in the show notes. So thank you very much, Planet. I really appreciate your support. Hey, Qiusheng, welcome back to the podcast. Thanks for coming back again. Really, really appreciate it. The previous episode we created together has been downloaded, I can't remember how many thousands of times, maybe 8, 9, 10,000 times. So people really enjoyed it. People really interested in the work that you do. Just for a quick recap for those people that haven't listened to you before, you're an associate professor in the geography department at the University of Tennessee in Knoxville. And you are the creator, I guess we could call you, of something called GeeMap. How did I do with that introduction?
It's great. Yeah. Thank you, Daniel, for the invitation. And I'm very honored to be here again on the Mapscaping podcast. And I'd love to talk more about GeeMap and Google Engine with you and the audience.
Perfect. That's exactly what I want to talk about today. So that this is going to work out great. Let's start with a very obvious question. What is GeeMap? What does it do?
GeeMap is a Python package, open source Python package for interactive visualization and analysis with Google Engine. So you build on top of the Google Engine Python API for doing computation, and also utilize a couple open source mapping library for doing visualization. So essentially, you can do large scale computation using Google Engine, using the browser. And in the meantime, you can easily visualize data in a Jupyter environment. So it makes it really easy to do with Carbonite code. Essentially, it's like help you watch a movie on the internet using a browser, but it's like you don't have to worry about how to have a good server, a good computer. All you need is just a browser, so you can do that on your laptop, on your cell phone, or even on your tablet. Yeah. So that's essentially what GeeMap is about. It's computation and also visualization.
Why did you make this? It sounds like I've seen this in action, and it looks not complicated. That's not the word I want to use, but you put a lot of work into it. It looks like you put a ton of the work into it. Why do we need something like this? Why, you mentioned it's kind of bridging these gaps, but wasn't there anything that did that before?
Yeah, I'm glad you asked. So basically, it fills the gap of the kind of limitation of the Google Engine Python API. So you can think about the Google Engine provide multiple APIs, the JavaScript API, Python API, and also the REST API. JavaScript API has the most comprehensive documentation on the website. So Google Engine release started 2010, so it's over 13 years now. And so JavaScript has always been the kind of the first class citizen of Google Sensing because what they provide with documentation, examples, and a lot of tutorials. So when I started using Google Sensing in 2017, at the time, Python API was quite limited. So you can think about the API has two components, computation and also visualization. And JavaScript API has both. So you can do computation, you can also visualize the data interactively on the map. So using the Google Earth Engine code editor. It's very easy to do. And then, but Python is mostly just computation. So you cannot actually visualize any data on using the Google Sensing API because it doesn't provide native support for that. And so I'm really into Python. I teach my students how to use Python, but at the time when I'm teaching the courses, it's like there's no way you can visualize the data easily. So in the meantime, I'm also use Google Sensing for research, and I had to figure out a way actually how to like visualize the data. So I kind of go back and forth. So I started learning JavaScript, the Python API, the Earth Engine JavaScript API. I didn't like it, so I went to Python. But at the time, you can only print out a thumbnail, so you cannot really visualize data interactively. And then it's just too difficult because there's not a lot of examples on their documentation website. So I went back to JavaScript, didn't like it, and then I went back again to Python. So at the time, I noticed like, oh, there are Folium. You can actually pull the data layer, visualize it using Folium. And then later on, IPyLeaflet and some other mapping libraries, and also IPyWidget. So I learned a couple like open source packages that makes it feasible for me to visualize the data. And then, so I released the Python package. Initially called GE Hydro. It's because I'm doing more like hydrological studies. I create a package just for trying to like make it easier to visualize the data. But later on, because I was teaching my students and also I saw that maybe I can generalize that to make it more available to the geospatial community. So I renamed it as GeeMap. And then, so in the meantime, I'm teaching my students. I'm also developing packages. So I add some new features and then I teach my students next day in class. And then, so I do that for a couple months during the teaching. And then after I post it on GitHub, people like it and then comment and then they see some of the videos, demos that I produce. And then people start using that, providing feedback, and the rest is history. So I continue to add features, improve it, release new version pretty much every week or two. So that's kind of a long story. Is that I want to use it. It's not available. I want to use the functionality to visualize the data because if you're doing geospatial, if you cannot zoom in and zoom out, you cannot see the data interactively. It's not very interesting. So that's why I spend a lot of time trying to make it easier for myself and for my students. In the meantime, also for the geospatial community, if people find it useful for it, if not, yeah, at least it benefit myself and my students.
Yeah, so that makes a lot of sense. If I had to summarize this, I'd say that you looked at both these APIs. JavaScript didn't do what you wanted to do, and you were used to working in Python. So you thought, if I could just, I already have the computational capabilities in Python that I need. Great. What I'm missing is the visualization side of it. So you went ahead and built that in Python. So this means for a Python programmer like you, Python developer like you don't have to leave the Python environment. You can just stay using the code that you like using and do both of these things. Like I'm not a developer, at least not the developer that you are. Could you explain to me what happens when I use GeeMap? Like, can I run a process, create some data, do some analytics, and then visualize this? And when I visualize it, is it just an image I'm getting back? Like what you're talking about? You're talking about the thumbnail with JavaScript, or does this visualization come back in a map viewer, like what I might be used to with other web mapping tools, where I can zoom around and pan in, click on a pixel, get some information, that kind of thing?
Yeah, exactly. So as I mentioned earlier, the API has two components, computation and visualization. So the general workflow would be, so if you're using Python, you will most likely need to import a package. So you will start with import GeeMap, and then you create an interactive map using one of the mapping backends, for example, Folium or IPyLeaflet. So the default one is IPyLeaflet because it's provide the most functionality because it has so-called bi-directional communication functionality. That means if you click your mouse on the map, you can get the coordinates. You can use the coordinates or whatever to do computation. For example, you can select a polygon and you can use the polygon to do some, for example, zonal statistics, or you can clip the images. So basically you can pass back to the program to do computation. And so once you create a map, you can load some data. So all the data, so Google Sensing has a huge data catalog. It's called the Earth Engine data catalog. So that one right now has over 90 petabyte of data. So basically 90,000 terabyte, and it's increasing daily. And so basically, it's you can imagine that the analogy I would give is that you can watch any movie for free. For example, the entire Netflix database or the whole universe, all the movies are free for you to watch. But it's in the geospatial domain. That means all the satellite data, all the geospatial data in the public domain, many of those, the most popular one, are already included in the Earth Engine data catalog. So all we need to do is that figure out what's the unique ID. So kind of every images, every data set in the Earth Engine data catalog has a so-called asset ID. You can think about like social security number in the US, right? As long as you know the ID, you can just pull the data in, just one line of code. You can point to the data set, and then you can just use GeeMap, just like add layer, and then you can pass in some visualization parameters, and then you can visualize that. Basically, you can change the color, you can change the band combination. If there's a single band, you can change the color palette. So in that way, you can pull the data in. So Google Sensing is different from traditional remote sensing. When you're visualizing the images, you are actually downloading the images or have the images locally and then access the data. But Google Sensing is like cloud computing, all the data in the cloud. So essentially, you are streaming the data on the fly. You're not actually downloading data. Exactly the same like you're watching a movie on Netflix, right? You are not actually downloading the huge data set because most of the data set in the data catalog are pretty big. So you're actually just visualizing that using basically the tile layer. So what you see on the browser is a data layer that's passing as a base map layer, kind of like similar to Google Map or Google Earth. You can zoom in and zoom out. It changes the resolution dynamically. So it's pulling the data, so it's compute on the fly. And this why it's so fast. So it's not downloading. They say you have a 1 gigabyte imagery. You're visualizing it. It's not downloading the whole gigabyte. It's based on your map view, your area of the map, and also based on the zoom level. So if you zoom out, for example, at a global scale, it's not using the native resolution. So you might using, for example, 10 kilometer instead of 30 meter. When you zoom in, your area becomes much smaller, but your resolution might become larger. But still, it's a small area. So under the hood is basically pulling the tile layer and transport to the client. So under the hood is like a bunch of PNGs. So downloading the map tiles and then display on the map. So whenever you're doing the computation, it's running on the server in real time and then transport to your browser using a tile layer. And that makes it really, really fast. So kind of workflow is that create an interactive map and then pull the data layer, the original data source, if you want to visualize that. And then you can run some computation. For example, if you want to, let's say, extract the vegetation, right? You can compute some spectral difference in the indices. And then you do some thresholding or do object detection, whatever you like. So in between, you can have very complicated algorithms, or you can have some very simple one. And then once you get the result similarly can be just pulling as a data layer. And then you visualize the data layer, you display the map, that's it. So kind of overall workflow is something like this. It's pretty simple and straightforward. And of course, GeeMap has a lot of tools that makes it easier for you to, for example, you can compare data layers side by side. You can have a time slider to visualize time series images. So many of those are actually very simple to do, just with 1 or 2 lines of code, compared to JavaScript that you might like need to write hundreds of lines of code to do the same thing. So that's why kind of GeeMap is kind of popular in the community, because it simplifies a lot of process. Because similar to the streaming services, right? Now everyone like watch movie on YouTube, on Netflix, Amazon Prime, whatever, right? People don't go to buy the DVD anymore. So exactly the same, just like we are using cloud computing, and you also want to have some tools to be able to actually do the computation and visualization easily, rather than you have to go to the data portal, for example, NASA, USGS, to download the data to your computer and then try to like load the data. So if you're doing global scale studies, it's going to be huge. It's going to be terabyte of data. Even if you have storage, you may not have the compute. You may not have enough memory to handle those large data sets. But now with Google Sensing and also GeeMap, you can do global scale computation, and then you can use GeeMap, for example, to visualize the data easily, just with a couple lines of code.
So this is going to sound like an incredibly naive question, but I'm hoping that it leads on to a discussion about client objects and server objects, and hopefully you can define that a little bit more for us to make it clear to the audience what's possible with both of these different types of objects. How is this different from like a plugin that I might use that connects to Google Earth Engine in QGIS or ArcGIS, for example?
Yeah, so for desktop, for example, ArcGIS, QGIS, so traditionally those are more like desktop GIS or desktop computing, because when you are visualizing the data, you already have it locally. Of course, now because of the cloud native geospatial, so for example, cloud optimized GeoTIFF, or some of the data right now, you can actually, those desktop GIS can also visualize data directly using the HTTP browser, but still, they cannot really handle a large amount of the cloud data. So in contrast, Google Sensing is a totally different platform. So it's purely cloud computing. Everything is in the cloud. So in the differences between client-side object and server-side object is, so the client side, so all the things live within the browser. Only you can actually inspect the results. Server-side object, it means, think about the images. Let's say we're trying to visualize a global DM, for example, 30-meter resolution, right? So if you're trying to do it in QGIS or ArcGIS or other desktop GIS, you need to actually have the data on your computer. So that one, if you read it using, for example, raster.io or any Python packages, you are loading the entire image into the memory. So for example, if this 10 gigabyte, you are loading 10 gigabyte into the memory. But for server-side object, we are not actually loading the entire file. So you're only pointing to the image. And then when you are visualizing, you're only requesting the tile. So it's changing dynamically. And so you cannot actually use desktop GIS to run computation on the Google Sensing object, because that one is more like, you can think of like a black box. Only Google Sensing understands how to process that. If you want to get the data out, you need to export as a NumPy array, but it only allows you to actually extract a small area. If you're getting a large amount of data, it's going to be pretty slow. Analysis will be like this. If you're trying to watch a movie, you can either watch the movie locally if you have the file, or you can use the browser to watch the movie. But imagine the movie itself is not exposed to you. You cannot directly download the movie from Netflix, right? You're only watching it. So under the hood, there are a lot of infrastructure, a mechanism to stream the data to your client side. But it's more like doing streaming. You're not downloading. If you have a high definition movie, it's like 50 gigabyte. You're not downloading the 50 megabyte all at once to your computer. So that one you can think about is a server-side object that their server understands. And you are requesting, for example, if you are fast forward or you change the time slider to a certain point, it's based on a request. It's send back the request to the server and then request next specific frame to your client so that you can see it. So in the cloud computing, it's the same thing. So those client-side objects, so it stay in the Google Sensing data catalog. In the server, you can request it. Of course, you can request the entire images, but it's going to take you a long time to do that. But if you're only visualizing a small portion, it's really, really fast. So you need to make sure that it's very important for new beginners coming to the cloud computing. You need to understand which one is the client-side object, which one is Python. So server-side object, because for most of the Python programming, it's actually client-side. So you're defining a variable. You can see the variable, it lives in your memory. But for Google Sensing, you can also define a variable pointing to a 10 gigabyte image, or you define a variable pointing to the entire Landsat 9 image collection. So that one contains, for example, millions of images, and the variable is not hosting that entire image collection. It's just pointing to that. So it's more like a reference. Eventually, you have to actually get a small piece, some metadata information, or you can inspect it if you want to.
Does this then mean that, through these different plugins, if we stay with QGIS and ArcGIS for a second, they connect to Google Earth Engine, that I can visualize data from Google Earth Engine in my QGIS, ArcGIS environment, but I can't do analysis. So it's just a visualization thing, and then I can do my analysis with my local data on top of that. But in that situation, it's just visualization. But what you're talking about with GeeMap, for example, I can do both. I can do my compute and I can do my visualization. And if I have local files, I can also add them to my GeeMap. I can show them, but in that situation, they're also just visualization layers.
I think yes and no. So actually, you can think about GeeMap and QGIS. They are pretty much the same, doing the same thing, accessing the Google Sensing, using it for cloud computing, but it's visualizing For GeeMap, it's just using the browser in a Python environment. In QGIS, you can visualize it. You can also do computation, but the computation need to use the Google Sensing API. You cannot use like tools, QGIS processing toolbox to process the imagery. That one doesn't work because you can think about the data layer that you pull into the QGIS. It's just a base map, so it's no difference from you're putting an OpenStreetMap. It's the same thing. It's just a base map. It's just a tile layer. But in the QGIS plugin for Earth Engine, there's a way you can actually write scripts, and then you can send commands to Google Engine for doing computation. So essentially, GeeMap, QGIS, or ArcGIS, those plugins can do the same thing. You can do computation, you can do visualization. The only difference is that you need to install, for example, desktop GIS. It's going to be gigabyte. For GeeMap, it's a browser-based, so you can just run on Google Colab. So GeeMap has been pre-installed in Google Colab, so you don't need to install it. But you can use it in any Jupyter environment. So it's a more like a lightweight browser-based environment. But if you really want to, they can do the same thing. But GeeMap certainly is easier because it's designed specifically for working with Google Sensing. So it has a bunch of tools available. And for ArcGIS support, so I already added support for ArcGIS Pro, so you can actually enjoy everything that you can do with GeeMap. QGIS plugin was developed by Gena, so he already joined Google, but that plugin is more like most for computation. It doesn't have the interactive widgets like GeeMap, so it's more like write script for computation and then just visualize that. But there's no like toolboxes that you can like, okay, turn the layer on and off or something like that. Then you will need to utilize the QGIS tool set. But again, the tools that, for example, ArcGIS toolbox, QGIS toolbox, those cannot process Google Sensing data because you need to use the compute API provided by Google Sensing to process the data. If you really want to use that, you need to export the data out. Then you lose the benefit of using cloud computing. Then the data becomes locally. It's not scalable.
Yeah, you can tell by my line of questioning here that I'm pretty new to all this. So I appreciate you sort of walking me through it. Let's say, for example, I have some local data that I want to add to my analysis. What do I need to do?
So two ways. So for GeeMap, GeeMap support both visualizing local data and also Google Sensing data. So if you simply just want to visualize data, combine multiple data layers, because some of the data are locally that's not available on Google Sensing, you can just create a map. You can add data from Google Sensing. You can add data locally. So in GeeMap, for example, you can just map.add raster. You can add any local raster data. Map.add vector. You can add any vector data. You can also add like cog layer. So you can add data directly from the cloud optimized GeoTIFF, but it's not in the Google Sensing data catalog. So for example, you can pull data cloud optimized GeoTIFF or spatial temporal asset catalog or stack from other platform anywhere you can access. So basically GeeMap support a variety of sources. But if you want to use your local data for computation with Google Sensing, then you will need to convert your local data to the cloud server-side object. So GeeMap has some functionality that allows you to do some conversion on the fly. So imagine if you have some local dataset, vector data, GeoJSON, or some like small vector data, GeeMap can do the conversion on the fly to convert it to Earth Engine object. So for example, GeoJSON, you can say GeoJSON to EE is going to convert to Earth Engine object, or Sapphire SSP to EE, or vector to EE. So there are a couple like a handy function can help you do the conversion. But the caveat is if your file is big, if you have like more than 10 megabytes, it's not going to work. So you need to upload the data to your Google Sensing account. And there's a Google Earth Engine code editor that allows you to upload some data. So that one has a larger limit. And so one analogy I would give you is that imagine you have a movie, a high definition movie on a local computer. You want to share with somebody else, right? How do you do that? You can upload to Google Drive and then you share a link with somebody, but it's not going to be instant. So you have to take time to upload it and then it's going to be optimized. Same idea like this one here. So if you have a movie, it's not going to be like upload the data set and then you can boom, convert on the fly instantly to Google Sensing and then optimize for cloud computing. It's going to take some time. But if you only have a small one, you can imagine that, okay, maybe Netflix like design a new feature that allow customers to share a movie with their friends, right? So you can have a small thumbnail, like small couple megabyte, just like social media, you can just drag and drop, and then that one becomes available on the server, and then you can share with other people. But if it's 10 gigabyte, 20 gigabyte, it's going to take some time for you to upload and then optimize. So that's kind of the similar mechanism. So for raster, right now, we don't have a way to automatically convert raster to Google Engine object. So only for vector. Vector, because it's GeoJSON, you can pass as a string and then convert to Earth Engine feature collection. But that's better than the JavaScript API, because JavaScript API doesn't even have that functionality. So the JavaScript code editor is limited to the browser. There's no communication getting data from your local computer to the browser. But GeeMap can pull, you can use Python to read any data from a local computer. And if it's small enough, you can convert on the fly. If it's too big, it's going to throw an error saying that it's too big. And then you can either simplify your vector data. For example, if you have too many vertices, if you have a country boundary is too big, you simplify. And then if you only have a couple like vertices, usually there's not a problem. So this actually provides a way that quickly you can do some testing, but you don't want to spend time to upload the data to the Google Engine server. It's certainly doable.
Okay. Just out of curiosity, what does that mean for that data that I upload? So you gave us a few different paths to uploading data, depending on the file size. Does that mean that once that data is uploaded to Google Earth Engine, is it visible to everyone or just to you?
No, it's just to you. So there are two ways. If you're doing conversion on the fly, everything is in the Google Engine server temporarily. So once you close the browser, everything is gone. So it's not permanent unless you specifically export the data to your account. Because every account, you used to have 250 gigabyte, but now they transform to like using cloud projects. So it's like use whatever quota that you have for the project, but everything is temporary. So most of the things are only readable. So it's not writable. So any data set on the data catalog, everyone can pull in, do some computation. And if you don't save the result, everything will be gone when you close the browser. But if you export it to your local account, you can also export to your Google Cloud Storage. You can export to Google Drive, or you can also export locally. So there are multiple ways you can do that. GeeMap also makes it easy for you to export, for example, a lot of images, entire images collection. But if you upload data to your Google Engine account using the Google Engine code editor, then it's permanent. It's for you. But you can choose to share with the public, or you can choose to share with a specific group. It's very similar to the Google Drive. You can upload files to Google Drive, and then you can choose whether to make it public, or you can share with some email, or you can share with a Google group. So there are different ways that you can share with the data. And if you share a script that access that data set, if other people if they don't have the permission, it will throw an error saying that it doesn't exist, or you don't have the permission to view the images. So they basically have like security control about the data, how it's going to be shared with different groups of people.
Yeah, that makes a lot of sense, especially the analogy back to Google Drive. Like I think most of us should have worked with that at some stage. So yeah, appreciate that. Exporting data, you mentioned it briefly there that you could export to these different places to your account on Google Earth Engine or to your local computer, for example. Are we limited in the kinds of things we can export, like the kinds of file formats we can get out and perhaps the size of them as well?
In terms of raster, so in the past, it support export to GeoTIFF or cloud optimized GeoTIFF. In terms of vector, you can export as GeoJSON. You can export as shapefile. What else? You can also export as CSV if you don't need the geometry. So that's kind of a traditional way. Then you can export to Google Drive or locally to Google Cloud Storage. But in the last Geo for Good summit in October, early last month, there's a new package called XEE. So you can actually export data to Xarray, basically large images collection. So those are more like for lazy computation. So imagine, because Google Engine, the data in the Google Engine data catalog is not the original file. So it's actually some kind of virtual mosaic. There's not a single, think about if you're doing the computation. So you're creating, for example, a cloud-free mosaic for the entire globe. And under the hood, there are like thousands of images all together. And on their server, there's not a physical file actually exists. So it's more like a virtual file somewhere in the cloud. So if you're trying to export like huge images, virtual mosaic, it's going to take a while because
Yeah.
you need to grab all the data, and then if your computation has a lot of like steps and it's quite complicated, it's going to take even longer. So if this is the case, you probably want to export to Google Drive to cloud storage because you can. I think it will allows you to export like 24 hours, for example. If it's more than 24 hours, you're going to exceed the limit and it's going to time out. But my recommendation would be if you're trying to use this cloud computing platform, try to maximize your workflow to do everything, the computation finish in the cloud, and you only export a small section or summary results rather than trying to export the original data. That defeats the purpose of using cloud computing because you are using cloud computing as a data downloading platform rather than as a cloud computing platform. Because imagine you're trying to do, let's say, if you have a population density image, you're trying to calculate, for example, the population for each country. So you're not supposed to download the entire images because that one can be very, very big, like many, many gigabytes. Instead, you should do the computation and then you do some zonal statistics using Google Sensing or GeeMap. And then you get for example, the population count for each country. And then you download just the number rather than original images. This much a smaller size. And that usually takes seconds or maybe within a minute. If you're trying to download the original one, it's going to take you hours. And that's usually not recommended way to do. So get the summary, avoid downloading large amount of data. It certainly is possible, but you can think about it's a free resources. Kind of like, let's say we are trying to watch a movie in a theater. It provides movie free to everyone. You need to wait in line. Otherwise, all of a sudden, you trying to block everyone else, and then only you want to watch the movie in the theater. It's not going to be feasible because it's a common resource shared by everyone. And whatever you are downloading, the large amount of data, it takes the bandwidth. So you can only have a certain number. If you use more than that, you're going to slow down, or they eventually going to ban your account if you use multiple accounts to do that. So that's kind of something you need to keep in mind when you're trying to export large amount of data from Google Sensing.
I mean, it makes a lot of sense, and I appreciate you always coming back to this analogy of movies. I think everyone's watched the movies, so it helps me understand it. I want to move on from GeeMap in just a second, although I realize there's a bunch more things to talk about with it. But what am I missing? Like, what am I not asking you? What do you wish people understood about a GeeMap?
Good question. I have not thought about it before. So, I mean, GeeMap basically is not like, it cannot do everything. So it fills the gap of visualizing the data. So it certainly, but if you are a Python user, you really want to use Python, then GeeMap is a good starting point you can utilize to do integration with your workflow. But it certainly cannot because GeeMap has the same limitation that Google Sensing has. So cloud computing doesn't solve everything. Cloud is not suitable for doing everything. So one simple example would be if you're trying to do some hydrological analysis, if you're trying to delineate the flow path or flow direction, delineate the watershed, those kind of things Google Sensing is not suitable for. So Google Earth Engine is especially good for application that doesn't rely on something far away. So especially if you're only doing your same location, you're doing time series analysis, that's perfect. But if something is related to something far away, then it's more difficult to separate them into smaller pieces to do parallel computing. Because if I delineate flow paths, if one drop of water in the mountain is going to flow like all the way to the ocean, you need to actually trace down all the flow paths. So it's not easy you can subdivide into smaller types to do computation. So there's something that right now is not suitable for. If you're doing that kind of study, you still use Google Sensing to do computation. And then you can export some intermediate results. For example, you will process the DM, do some filtering or whatever, and then you can export the data out and then still use some traditional tools to do computation. And also in terms of computation, it relies on the Google Sensing Python API. So you need to get familiar with the Earth Engine Python API. But it's relatively easy to learn. Everything is like EE doc something. So that means it's a client-side object. It's wrapped within the Google Sensing server. And your algorithm need to build on top of that. And also, I mean, for new users, even if you already know Python, you need to keep in mind is that Google Sensing is different from client-side computing. So similar in the Python world, right? When you're trying to do something repeatedly, you're writing a for loop or you're writing a while loop, and then you're trying to loop through. In the cloud computing Google Sensing, you should avoid using the for loop because you're doing the for loop. It's like in sequence. You are doing the computation, you need to wait for the next one. So it's not actually parallel processing.
Yeah.
For Google Sensing, it's like doing so-called a map functions. The map basically means it can subdivide the images into thousands of smaller tiles, and then each tile is sent to a server and then doing the computation and then return the result in seconds and then visualize that. So you should pay attention to some of those things that are very different. So once you know that, the nice thing about Google Sensing is that you have a huge data catalog. So you can use any data you want. And also in terms of computation, it's really fast. You can do things at a global scale. So in that way, I mean, for us as scientists, you can focus more on addressing the scientific question rather than spending in the past like 70-80% of the time trying to manage the data, trying to download the data, store the data, and then do some pre-processing, remove the cloud, and then trying to do computation. Even if you can do computation, you can do it in a smaller area. You cannot do it at a global scale. But now, so Google Sensing and cloud computing platform do the heavy lifting. So you don't have to manage the data. You just focus on, for example, if you're trying to do forest change analysis, right? Now you can just pull all the data in. You can run your algorithm. You can develop perfect algorithm. And then you can scale it up to the entire globe as long as your algorithm works. So you don't need to worry about like area all the time because you have access to the entire data catalog that has the global coverage, and you have time series back to like decades. So now you can actually do whatever you want. Kind of like the entire movie database is for free. And there are different categories of movies, actions, romantic, or whatever. You just need to figure out what do I want. Do I really into this action movie? You can pull out all the action movies and then you can run your analysis. You can figure out, for example, who are the main characters, how many movies appear like in there. You can run some statistics, something like that. But in the past, it's not possible because if you want to do that, you need to have your entire movie database on your local computer before you can do something like that. But right now, all you need to figure out what do I want, and then you think about how I'm going to do that. Because you know each movie has an ID. You can point to that, and then you can ask it, Google Sensing to do computation. For example, tell me, how long does that character appear in that movie? So essentially, for example, how many images intersecting with this location? How many images passing this location with cloud coverage less than 10% during the last 40 years? You can do that easily, just one line of code.
Wow.
Or you can tell that, okay, I want to create a cloud-free images for the state of Tennessee. Every year, annually, for the past 4 decades.
Yeah.
In GeeMap, it's one line of code, one line. It's essentially one line of code. But imagine if you're trying to do this traditionally, you have to download the data and then figure out, which do the intersection and then, okay, figure out the cloud. But how to actually merge them together, right? You need to actually, if you have an image, like 20 images covering the same location, some images might have cloud, some might have not. And then there's no perfect images. But in Google Sensing, you can just do a simple medium filter. So Google Sensing, like I said, is cloud computing that it deals things with each pixel. Kind of like if you go to Google Earth, right? You go to Google Earth, you zoom in, right? Looks perfect. There's no cloud. There's not a single cloud if you zoom in. Those are all actually kind of fake images. They're not real because under the hood, it has been processed by either Google Sensing or some other cloud computing. So every pixel is the best quality pixel for that location during a specific time period. And when you put all the pixels together, it looks perfect, but they don't come from the same images. So that's one thing that right now, why it's so fast, because it can do cloud computing. It can just subdivide this, send to a server, and then do the computation, get the base pixel, return, and then you put them all together, and then you can export the result rather than having to like process the images by image. This is by pixel. So your pixel can be, the resolution doesn't matter. It's like by pixel, every location is being processed separately. And this is like really, for beginners, they might not understand, okay, how do I do this? How do I do that? But you need to understand like how it actually works. And that's really helpful. They can understand what kind of things are best suitable for Google Sensing or Google Sensing most suitable for. What kind of things are not suitable for. As I mentioned, pixel-based, location-based, perfect. If something related to something far away, it's not very good because it's not very scalable in Google Sensing.
So I'm used to people like you talking about this stuff. I talk to a lot of different people that are doing a lot of different interesting work, right? But it still blows me away that this is possible. Like you were saying, that just take the best pixel from that time period across the entire globe and one line of code to make a cloud-free image of the world. It's insane to me. I wanted to ask you, so GeeMap Google Earth Engine, in my mind, is focused on raster data. And Google has something else called BigQuery, which focuses on vector data. Do you see, is anyone building a bridge to those two things so we can use both these engines interchangeably, or can you imagine that happening in the future?
Yes, it actually already has. So in the last Google Earth Engine, the Geo for Good Summit, they already released. So the connectors, the Earth Engine team and Google are building that. So as you mentioned, Google Earth Engine is best suited for raster analysis. Vector, they can do some, but it's not like super efficient. So BigQuery is one of the, potentially, because we're getting more and more large scale vector data. For example, the entire building data set of the entire globe, that one is like 200 gigabyte, right? It's not going to be able to handle by a consumer laptop. So they still also need some kind of cloud computing. So BigQuery, potentially, there's still a lot more work can be done. But right now, at least they have some way to actually to pull the data and then do some interaction with Google Engine. And also there are other open source alternatives, although it's not optimized for cloud. For example, DuckDB, the one that I recently started using it last couple months, it can also do a lot of like process data in the cloud, Parquet or GeoParquet format. They can do it very, very efficiently. So I'm very excited to see and there are a lot of like also startups doing some kind of this kind of cloud computing for large scale vector data. And there are a lot more improvement can be done in this aspect. And hopefully in the future, we can do vector data analysis very easily, similar to doing raster data analysis in Google Engine. So you can easily analyze like gigabyte, 100 gigabyte data, and then you can get the result in seconds. That would be amazing.
That would be amazing. I look forward to that future. When I said earlier I want to move away from GeeMap, that was pretty clumsy. What I wanted to say was I want to talk a little bit more around GeeMap as a project. So this is open source, right?
Mm-hmm. Yes.
Yeah. Has it been officially adopted by Google?
Yes. So Google. So I started working with the Google Engine team during the summer. I think started with in June 2023, and then up to October 2023. So like 5-6 months. I've been working with them. So basically, Google Engine really the Earth Engine team wanted to improve the Python functionality for the API. But as I mentioned, right now, they don't really have visualization. And so I started the project in March 2020. So it's more than three years and a half right now. And so it already have kind of quite a large user base. And so Google Engine reached out to me saying that can we work together to basically improve the support and also help supporting GeeMap because it's more like the community project. I think, yeah, I'm more than welcome to any contribution, but because they don't have the resources to support everything in GeeMap, and they can only support the core visualization functionality. So for example, visualizing the data layer, inspector, plotting the chart, or some of the interactive tools that you can use to draw a polygon or something like that, similar to the JavaScript code editor. So I've been working with them since June 2023. And then, so what we did essentially is reorganize the package into two components, the core functionality and also the actual functionality. So the core features basically means the Google Engine team help maintain and develop. So it becomes more stable, and the actual functionality will be developed by me and also the community. And of course, the Earth Engine team member, they're also contributing to those. So we spent a couple months meeting every week, reorganize that. And thanks to Justin and Nate, so those are the two Googlers that I worked intensively during the last couple of months. And then also a few more engineers from the Earth Engine front end team to help basically make those interface. But for GeeMap users, it looks the same. There's not really much difference. But under the hood, there are a lot of like core improvement, reorganization, restructure. And Google Engine announced it in the Geo for Good Summit in October 2023. So now if you go to the Google Engine documentation website, for most of the example, you will see JavaScript, and then you will also see the Python. So the Python example, you will see when you expand the code block, you will see import gmap.core as GeeMap. So basically the core functionalities is right now the Google Engine team helps support and maintain. So it becomes so much better because I'm not a computer scientist by training. I learned all the Python programming last couple of years because I have to teach it. Wow. So when I initially started the project like 3 years ago, I was like beginner. So I didn't really know a lot like how to improve. But over the years, I've added a lot of functionality. It makes some of the things are quite complicated. So it has been a pleasure working with the Earth Engine team to reorganize, restructure. And then now it looks so much better. And I'm so happy that it has been officially adopted. So if you go to the website, Google Sensing documentation, now you should see GeeMap there. Import gmap.co as GeeMap. But you can just import GeeMap, so you add all the extra functionality. So under the hood, the extra, basically GeeMap depends on the GeeMap core. So all the core functionality visualization, if they improve it, you can also use it in the GeeMap. So right now, basically, it's so much better than when I initially started. And thanks to all the collaboration and also the help from the Earth Engine team and also the Google front-end team. And another good news is that it has been officially adopted and also pre-installed in Google Colab. So now you can go to the Google Sensing documentation or GeeMap website. Anywhere you see like open in Colab, you can just click the link and then you can open the novel examples in Google Colab and then you can just run through that. You don't have to install anything. And another nice feature like the Google Colab team added was allow you to save your secrets. So basically your tokens in the notebook. So in that way, you don't have to authenticate every time. One of the annoying features in the past was like if you want to use Google Sensing, initially you have to install a package and then you need to authenticate, click like 7 or 8 times the buttons and then authenticate. But now it's just like open it, run it. If you already have a token, save. Next time you just everything can just run without having to authenticate or install anything. So it saves so much time and it's very good for doing teaching or workshop because you can, like I said, you have access to the entire 90 petabyte of the Earth Engine data catalog. And also there's another Earth Engine community data catalog maintained by Sam, my friend. And essentially like you have access to the entire catalog of geospatial data for free and you can use it to do any computation. So the analogy, like if we give somebody the entire movie database for them to watch for free online, I mean, everyone should try it out.
Yeah. Well, firstly, congratulations.
Mhm.
I think you've put a huge amount of effort into all of this, and then just to, I don't want to say give it away, but like give it to the community and say, here, there you go. I've made this and we can all benefit from it is, firstly, it's incredible. And secondly, it's greatly appreciated. I know a lot of people that use the tools that you've made really appreciate it. I see the way you show up online, the way you don't just make these tools, you also support them. You create a whole bunch of content around them, showing people, teaching people, not just your own students, but the world essentially. And I know that it's much appreciated. So thank you so much for all of your efforts. But my question is, what has this meant for you? Like, so you needed to do this or you wanted to do this as part of your work, to help you teach your students better, but you ended up teaching the world essentially. A lot of data scientists out there how to do it. What has it meant for you? What has it meant for your career? What do you get out of all of this work? Are there any direct, indirect benefits that you've seen?
Yeah, of course. I mean, I enjoy doing that. So actually, I'm not required to do that, but I enjoy doing that because it benefits my resource. So I build those tools actually to help my resource, make my resource easier, and also teach my students. So I have the content to teach my students because it makes it easier for them to learn. But the things that I do, like post it on GitHub and also YouTube, is more like by accident. I just put it out there because I might still need to install the packages. But initially, I'm very introvert. I'm very shy. I don't talk a lot, right? But the last couple of years actually changed my life. So because I started posting more content, but you really see my face on the internet. It's just a video. So all my stuff actually pretty easy. I just record the screen. I don't show my face on the most of the time on the video. But it opened up a lot more opportunities. More people get to know me, and then also lead to collaboration, funding, students. So certainly it's a huge benefit. So if you're really into that, I would encourage you to look at some of how are people doing that in the open source community. And what I'm doing is not groundbreaking. I'm only building on top of what other people build. But my mission is to make it easier, right? There are a lot of cool stuff out there in the open geospatial community, but not everyone are aware of those resources. So I always enjoy learning some new stuff and then integrate into my projects and then make it easier. But in the meantime, not just easier. You need to show people how to do it, how to use it, because anytime if I spend on some feature or something, I want people to use it because otherwise my time is not utilized. Only me, I'm using it. So if possible, I always create a notebook, for example, try it out. And I also usually record, for example, a short demo, a couple seconds, 10, 20 seconds, so like what it is, right? You need to actually promote so that people use it, but don't promote things like for the purpose of trying to be famous, because it's not something that you can get rich or get famous easily. But you continue to do what you're doing, but just don't do it like on purpose, because more like use it. I post things as a record so that I can send to my students later when they have a question. Okay, go to this video. So actually, it saves me time in the long run. Also, I try to make things easier so that other people can actually reproduce it, and also try to minimize the requirement. I want to be able to do everything online just using a browser, so that everyone around the globe, if they have an account, if they have a browser, they can do that rather than you have to install some huge packages on a computer. Because I came from a poor family, we didn't have money, we didn't have anything actually to eat. Rather, not to mention like to have a computer. I didn't have a computer until I went to college in 2003, learning like Windows 95 or something like that at the time. So I know there are a lot more people out there that don't have access to those fancy computer and configuration, but at least they have some kind of internet. So if they really want to do something, they can do it. So what I'm trying to do is to showcase how we can utilize those free resources, either cloud computing, open source packages, open data, right? So all you need is some time and patience. You don't need a fancy computer. You don't need to be very smart. But if you can dedicate some time to learn some of this, you can make an impact. So everyone can do that. I'm showing you, if I can do it, everyone can do that as well. So I like interacting with the community, getting the feedback for those projects and improve it. So if you have any questions, you're welcome to go to those GitHub repositories. Ask. You usually get a response from me within 24 hours. Free customer service within 24. But sometimes I'm too busy, so might not get a response. But I love helping the community. And connecting with the community. And if everyone's doing this, I mean, it'll be so much better, so that we can all help each other and make contribution back to the community.
Well, you are definitely making the world a better place for a lot of people. And again, it's really appreciated.
Thank you.
Where can people go? Like, so you mentioned a GitHub. Perhaps you could send me some links after this and I can include them in the show notes where they can go to either follow along with you or reach out or get some help. Do you have any places you could tell us about now? And maybe we can also include some other links in the show notes later. Yeah,
sure. So if you want to connect with me, you can follow me on social media. So the website is gishub.org, gishub.org. And I'm online everywhere. Twitter, Facebook, LinkedIn. You can find me. Just search my name.
TikTok?
To find. No TikTok. I have an account, but I don't use it. But mostly on Twitter and LinkedIn and some Facebook. So always posting content pretty much daily, if not daily, at least weekly. So you can see some of the things that I'm working on. And you can go to my GitHub repository or just search Open Geospatial Solutions. So they have all kind of packages that I created and maintain. So anyone are welcome to check out those repository and contribute. I always welcome contribution. And if you have any questions, you can check out those repository. And then usually there's a discussion board there. You can ask questions. And you can follow me on social media. I'd love to interact with you. If you have any questions, you're also welcome to email me at any time.
Well, Qiusheng, you are a legend, and I really, really appreciate your time. Thanks for talking with me today.
Thank you very much. It's my pleasure.
Thanks again to Planet for supporting this podcast episode. And by supporting this podcast episode, you're also supporting all of the podcast episodes that I've ever created. So I really appreciate it. Just want to remind you that Planet images the Earth every day to create a living dataset of global change. And you don't need to learn new tools or take a ton of time to make use of these insights. You can use Planet satellite imagery to drive richer analysis with high spatial resolution and high frequency data, broad area coverage and automated detection feeds integrated directly into your geospatial platform. You can learn more at planet.com/GIS, and you'll find a link to that in the show notes of this episode. Thank you very much for tuning in all the way to the end. It's much appreciated. I hope you enjoyed that episode with Qiusheng. GeeMap is well worth checking out. There'll be links to this also in the show notes of this episode, and also put a link to Qiusheng's previous episode that was a really in-depth introduction to Google Earth Engine. That's it for me. I'll be back again soon. I hope that you'll take the time to join me then.